Welcome to the Platform Engineering Playbook podcast, where everything you hear is built, reviewed, and improved by AI, by me, and by you, the listener. This show keeps me, and hopefully you, up to speed on the latest in platform engineering, SRE, DevOps, and production engineering. It's a living experiment in how AI can help us track, explain, and discuss the fast-moving world of infrastructure. Every episode is open source. If you've got something to add, correct, or challenge, head to platform-engineering-playbook.com. You'll find all the content and a link to the GitHub repo. Open a pull request, join the conversation, and make the playbook smarter. Let's get into it.
Today we're diving into a service mesh mystery that's challenging everything we thought we knew about performance. Istio Ambient reached GA in November 2024 with 8% mTLS overhead, compared to Sidecar's 166%. Impressive, right? But Cilium promised even better with kernel-level eBPF. Theoretically, processing packets directly in the kernel should beat user space proxies every time.
And then the October 2025 academic benchmarks dropped.
Exactly. Cilium showed 99% overhead. User space beat the kernel. What happened?
So we've got this counterintuitive result that demands explanation. And the answer reveals something fundamental about architecture design, that where you draw boundaries matters more than raw execution speed.
Let's set the stakes here. Platform teams managing thousands of pods are paying real money for sidecars. 250 megabytes per pod times 1,000 pods is 250 gigabytes. At AWS memory pricing, that's about $127,000 a year just for the mesh infrastructure.
Just for the proxies before you even count the latency penalty or engineering time managing them.
Right. So the sidecarless revolution promised to solve this. Two competing visions emerged, Cilium saying move everything to the kernel with eBPF, and Istio Ambient saying use purpose-built user space proxies. Radically different architectures.
And choosing wrong means either you're wasting money on inefficient infrastructure, or worse, your API server crashes when you scale to enterprise sizes. So this matters.
Okay, let's set the eBPF promise. What was Cilium trying to achieve?
The core idea is elegant. Traditional service meshes run Envoy proxies in user space. Every packet has to cross from the kernel into user space for processing, then back to the kernel to continue its journey. Those context switches are expensive. Cilium said, what if we process packets entirely in the Linux kernel using eBPF programs?
So eBPF programs are like little sandbox programs that run directly in kernel space.
Right. The Linux kernel has hooks at various points. When a packet arrives, when a connection is established, when data is sent, Cilium loads eBPF programs at these hooks to intercept traffic. For L4 processing, like TCP connections and routing, everything happens in the kernel. Encryption uses WireGuard, which is also kernel-based. The promise was maximum efficiency, no expensive transitions between kernel and user space for basic traffic.
And for L7 HTTP traffic?
That's where Cilium still needs Envoy, because HTTP parsing, routing rules, retries, that's complex application layer stuff. So Cilium deploys one shared Envoy proxy per node. When traffic needs L7 capabilities, the eBPF programs direct it to that shared Envoy running in user space.
So it's not pure kernel processing.
No, it can't be. Every service mesh has to handle HTTP eventually for observability, advanced routing, retry logic. The question is where that boundary sits.
And Istio Ambient took a completely different approach.
Yes, Ambient uses Z-tunnel like Zero Trust Tunnel. It's a lightweight proxy that runs per node in user space, not in the kernel. It handles L4 traffic, TCP connections, mTLS encryption, identity-based authentication, basic network policies. Crucially, Z-tunnel doesn't parse HTTP at all. It just treats traffic as opaque TCP streams.
So it's doing mTLS handshake and encryption without looking inside to see if it's HTTP.
Exactly. And when you need L7 capabilities, HTTP routing, traffic splitting, circuit breakers, you deploy optional waypoint proxies. These are full Envoy instances, but they're deployed per service account, not per pod. So if you have 1,000 pods across 50 services, you might deploy 50 waypoint proxies instead of 1,000 sidecars.
Okay, so we've got Cilium with kernel eBPF plus shared envoy per node, and Ambient with user space zTunnel plus optional waypoint proxies per service. Now let's talk about the benchmarks. What did the academic study actually measure?
The archive study from October 2025 was peer-reviewed research from multiple universities. They tested 4 implementations: Istio Traditional Sidecar, Istio Ambient, Cilium, and Linkdir, under production realistic conditions using 40O load generator at 3,200 requests per second with 200 millisecond backend delay, simulating database calls.
And the mTLS overhead results?
At P99 latency, Istio Sidecar added 166% overhead, Linkdir added 33%, Istio Ambient added 8%, and Cilium added 99%.
Wait, so Ambient, running in user space, had 8% overhead, while Cilium, running in the kernel, had 99%. That's 12 times worse, despite theoretically being faster.
Right, and if you look at CPU consumption, Cilium used 0.12 cores versus Ambient's 0.23 cores. So Cilium was using less CPU, but delivering worse latency. The bottleneck wasn't raw processing power.
So what's going on? Why does kernel-level processing underperform user space here?
The answer is the L7 processing boundary. Remember, every service mesh has to handle HTTP eventually. For Cilium, here's what happens. A packet arrives, the eBPF program in the kernel processes it, encrypts it with WireGuard. Great, all in kernel space. But then, if you have any network policy that requires looking at HTTP headers, or you want retry logic, or you need observability metrics, that packet has to be copied from kernel memory into user space memory, so the shared envoy proxy can parse the HTTP.
So even though the initial processing is fast, you pay the cost of that kernel to user space transition.
And then after Envoy processes it, the packet goes back to the kernel to continue its journey. So you're doing these expensive memory copies and context switches. The academic study found that when they disabled HTTP parsing entirely in Cilium's Envoy, throughput improved almost 5 times. The eBPF part was fast. It was the transitions to handle L7 that killed performance.
And Ambient avoids this how? Ambient's zTunnel is purpose-built for L4. It doesn't try to parse HTTP at all. When it sees a TCP connection, it does the mTLS handshake, encrypts a stream, and forwards it. Because it's not looking inside the HTTP, it can optimize that path aggressively. 8% overhead means the encryption overhead is minimal. When you do need L7 processing, the traffic goes directly to a waypoint proxy that's already in user space. No kernel transitions required. So Ambient accepted that L7 happens in user space and designed around it, while Cilium tried to stay in the kernel as long as possible, but got penalized whenever L7 was needed.
Right. And for most production workloads, you're going to need some L7 capabilities. Routing, observability, retries, these are table stakes. So Cilium's architecture hits the worst case more often.
Okay, but that's just latency and CPU. Istio also published large-scale stability testing. What did that show?
This is where it gets really interesting. Istio set up an Azure Kubernetes cluster with 1,000 nodes, 11,000 CPU cores, 50,000 pods running 500 different microservices with 100 replicas each.
That's enormous.
Yeah, way beyond most production deployments, which is the point. Stress test at the extremes. And they simulated production churn, replicas scaling up and down every second, namespaces getting relabeled every minute, constant service discovery updates. Both Ambient and Cilium were tested under these conditions.
And?
Throughput-wise, Ambient delivered 2178 queries per core versus Cilium's 1815. That's a 20% per core efficiency advantage, which translates to 56% more total cluster throughput when you multiply across 11,000 cores.
So Ambient was faster at scale.
But the bigger discovery was stability. Cilium's distributed control plane architecture, where every node runs a Cilium agent that independently talks to the Kubernetes API server, caused the API server to crash under that aggressive churn.
The API server crashed?
Yes, 1,000 Cilium agents all independently querying for service updates, pod labels, namespace changes. The aggregated load became unbearable. The cluster became unresponsive. Istio's centralized control plane, where a single Istio D manages all the Z tunnels, handled the same workload without instability.
So kernel efficiency doesn't matter if you can't stay online.
Exactly, and this reveals something important. Cilium's architecture makes sense at smaller scales. Under 500 nodes, under 5,000 pods, the distributed control plane isn't a problem. But if you're planning for enterprise scale, that centralized control plane design becomes critical.
Okay, so we've got the mystery solved. Architecture boundaries matter more than execution location. Now the practical question. When should you use each?
Let's build a decision framework. Start with cluster size. If you're running 1,000 to 5,000 nodes and you need proven 50,000 pod stability, Istio Ambient has the data. If you're under 500 nodes, Cilium's API server issues are unlikely to surface.
What about traffic patterns?
This is huge. If 70% or more of your inter-service traffic is L4, gRPC, database connections, message queues, and only 30% needs L7 routing, Ambient wins because you deploy Z-tunnel on every node and add waypoint proxies only for the services that need HTTP capabilities. But if your traffic is pure L3/4 with no complex HTTP routing at all, Cilium can be more efficient because you're not paying for L7 infrastructure you don't use.
Give me a concrete example.
Okay, e-commerce platform with 2,000 microservices. 80% of traffic is internal gRPC between back-end services, inventory, pricing, recommendations. 20% is user-facing REST APIs with sophisticated routing, retries, circuit breakers. With sidecars, you're deploying 2,000 Envoy proxies, consuming 500 gigabytes of memory, costing about $200,000 a year.
And with Ambient?
Deploy Z-tunnel on every node, say 50 nodes. That's 50 times 26 megabytes, about 1.3 gigs for the L4 layer. Then deploy waypoint proxies for the 400 services that need HTTP capabilities. That's 400 times 100 megabytes, 40 gigs. Total memory footprint is 41 gigs instead of 500 gigs. You've saved $186,000 a year in infrastructure costs alone.
That's a compelling business case. What about Cilium?
Cilium makes sense for smaller scale with pure L4 requirements. Start up with a 50-node cluster, back-end services communicating via gRPC, no complex HTTP routing. If you're already using Cilium for your CNI, the container network interface, adding service mesh features is incremental. Cilium's 95 megabytes per node is the smallest footprint you can get. 50 nodes times 95 megabytes is 4.7 gigs total.
Much cheaper than Ambient's 41 gigs in that e-commerce example.
Right, but remember, the e-commerce platform has sophisticated L7 requirements. If the startup tries to scale to 2,000 pods and adds HTTP routing, they'll start hitting the shared Envoy proxy bottleneck, one proxy per node handling all L7 traffic from multiple pods. Ambient's per-service waypoints scale better at that point.
And when should you just keep sidecars despite the cost?
I'd say 3 scenarios. 1, multi-cluster federation. If you're running services across multiple Kubernetes clusters in different regions or clouds, Ambient's multi-cluster support isn't mature yet. Sidecars are the proven option. 2, maximum isolation for compliance. PCI DSS, HIPAA, FedRAMP. If your compliance framework requires per workload security boundaries, sidecars give you a dedicated proxy per pod. 3, heavy L7 traffic per pod. If every single pod is generating significant HTTP traffic requiring per pod routing and retries, sidecars scale naturally because the proxy scales with the pod count.
So it's not that sidecars are obsolete.
Not at all. They're the most mature option. 7 years in production, extensive tooling, multiple vendor support options. If you're in financial services with multi-region deployment and strict compliance, the $200,000 sidecar cost might be justified by the maturity and isolation.
Okay, so let's say a team decides Ambient makes sense. What does migration actually look like?
Here's the reality check everyone misses. The technical migration is trivial.
You can swap Ambient for sidecars in minutes. Remove the sidecar injection label from a namespace, add the Ambient label, and Istio handles the transition. The organizational change is what takes 90 days.
What does that involve?
You've got to update CI/CD pipelines for every project. GitHub Actions workflows, GitLab CI configs, Jenkins files, anywhere you reference Istio configuration. Documentation needs updating, team training. Developers need to understand the new model, how Z-tunnel works, when to deploy waypoints. And you need gradual rollout. Start with 5 to 10 low-risk dev services, validate for 2 weeks, expand to production incrementally.
So it's the same pattern we saw with the Fidelity OpenTofu migration. Technically simple, organizationally complex.
Exactly. Fidelity migrated 70% of their 50,000 state files in 6 months, and they said the technical side was trivial. It was the change management that mattered. Same here. Budget 90 days to hit 30 to 50% adoption if you're aggressive, longer if you want to be conservative.
And what's the cost benefit on that 90-day migration effort?
If you're saving $186,000 a year on infrastructure and you allocate one senior platform engineer for 3 months at, say, $150,000 annual salary, that's about $37,000 in labor cost, plus maybe $10,000 for vendor support from Solo.io or Tetrate. You're still saving $139,000 net in year 1 and the full $186,000 every year after. That's a pretty clear ROI.
Okay, so let's bring this home. What's the key insight here for platform engineers evaluating service meshes in 2025?
The counterintuitive lesson is that execution location, kernel versus user space, matters less than architectural boundaries. Istio Ambient wins not because user space is inherently faster, but because it's designed around the reality that L7 processing happens in user space anyway. Cilium's kernel-level eBPF is brilliant for L4, but the architecture pays a penalty every time you need HTTP capabilities.
And scale matters differently than people think.
Yes, Cilium's distributed control plane is a feature at small scale, resilience, no single point of failure. But at enterprise scale with aggressive churn, it becomes a liability. The API server can't handle 1,000 independent agents. Istio's centralized control plane flips that. Potential single point of failure at small scale, but proven stability at 50,000 pods.
So the decision framework is cluster size, traffic patterns L4 versus L7, and your scale ambitions.
Right. Under 500 nodes with pure L4, Cilium wins on efficiency. 1,000 to 5,000 nodes with mixed L4 and L7, Ambient wins on cost and stability. Mission-critical multi-cluster with heavy compliance, sidecars win on maturity despite the cost. There's no universal answer. It depends on your specific constraints.
And the migration timeline is 90 days of organizational change, not a weekend technical swap.
Correct. The technology is ready. Istio Ambient reached GA in November 2024 after 26 months of development involving Google, Microsoft, and Red Hat. Cilium's been stable for years. The challenge is coordinating team training, CI/CD updates, and gradual rollout across your organization.
So platform teams need to do the math on their specific situation. Calculate your current sidecar memory cost, evaluate your traffic patterns, consider your scale trajectory, and decide whether the architecture fits your use case.
And recognize that this isn't a binary decision. You can run Ambient for cost-sensitive services, sidecars for mission-critical multi-cluster workloads, and Cilium for small-scale L4-only clusters. Mix and match based on requirements.
The architecture you choose matters less than choosing deliberately based on your constraints, which I guess is the meta lesson here. Don't assume kernel is always faster. Don't assume user space is always slower. Understand the boundaries, test at your scale, and make the decision that fits your reality.
And if you want the full technical breakdown, we've got a deep dive blog post with all the benchmark data, cost calculations, and migration playbooks. Link in the show notes.
The sidecarless revolution is here, but it's not about one architecture beating the other. It's about matching the architecture to the workload. That's the real engineering.
That's it for this episode of the Platform Engineering Playbook podcast. Every topic, transcript, and summary you just heard lives out in the open at platform-engineering-playbook.com, where anyone can suggest updates or add insights through GitHub. If you've got thoughts, fixes, or new ideas, open a PR. And if you enjoyed the episode, rate us on your favorite podcast platform. We're always shooting for 5 stars. While you're there, give the project a star on GitHub. It helps others find and contribute to the Platform Engineering Playbook. This podcast is generated by AI, reviewed by AI, me and you, a community of engineers keeping our craft sharp. Thanks for listening, and see you next time inside the Platform Engineering Playbook.